We are living through an energy turning point that is often described as a crisis, but it is better understood as a design challenge. For more than a century, modern life has been built on fuels that are dense, portable, and easy to trade. That system delivered prosperity, but it also created vulnerabilities, price shocks, geopolitical risk, air pollution, and a rising climate bill. The good news is that we do not need a miracle invention to change course. The real opportunity is to reorganize what we already know: how we use energy, how we move people and goods, and how we build power systems that are cleaner and more resilient. In this speech, I will make three linked arguments. First, the fastest and cheapest energy transition begins with using less through efficiency and smarter design. Second, the end of oil will not happen because we run out of it, but because better alternatives outcompete it. Third, the energy industry is shifting from a world shaped by scarce fuels to a world shaped by technology, and that changes who holds power, how markets behave, and how quickly progress can spread. Start with a simple principle. The cleanest unit of energy is the one you do not need to produce. Efficiency is sometimes framed as boring, but it is the highest leverage tool we have. When you make a building need less heat, you do not just save energy, you reduce the size and cost of every system around it: boilers, pipes, wires, power stations, and grid upgrades. The same applies in industry. Redesigning pumps, motors, and process flows can remove waste that has been treated as normal for decades. Efficiency is not about telling people to freeze in winter or sit in the dark. It is about better engineering and better choices: insulation, heat pumps, LEDs, smart controls, and high-performance motors. Most importantly, efficiency buys time. It lowers demand quickly, which makes it easier for clean supply to catch up. If we try to decarbonize by replacing every fossil unit one for one, we end up with an expensive race against physics and politics. If we decarbonize by shrinking the problem first, we make the transition cheaper, faster, and more reliable. Efficiency is not a sacrifice, it is system simplification. Transport is often treated as the hardest sector, but it is also where design can deliver dramatic gains. The biggest misconception is that transport decarbonization is mainly about swapping one engine for another. In practice, the first step is reducing the energy required to move a vehicle at all. Lighter materials, better aerodynamics, low rolling resistance tires, and improved drivetrains can cut energy demand before we even discuss fuels. This matters because every kilogram you remove reduces the size of the motor, the battery, the brakes, and the structure, creating a compounding effect. Once vehicles become far more fit, electrification becomes easier. Smaller batteries, longer range, lower cost, less strain on supply chains. But transport is also behavioral and spatial. If city design forces everyone into a car for short trips, we waste energy and land and we lock in emissions. If cities enable walking, cycling, and reliable public transport, we reduce car dependence and make electrification manageable for the journeys that remain. In other words, transport decarbonization is not a single technology change. It is a redesign of vehicles, streets, and choices. Electricity is the other half of the story, and here the same efficiency-first logic applies. A clean grid becomes easier to build when demand is flexible and predictable. That means efficient buildings, but also smarter timing. Shifting some electricity used to when wind and solar are abundant, and reducing peaks that force expensive backup capacity. This is why demand response, storage, and distributed generation matter. In a fuel-based system, the grid is built around large power stations and a one-way flow of electricity. In a technology-based system, we can create more modular networks, rooftop solar, community batteries, microgrids for critical sites, and local balancing that reduces the need for long-distance upgrades. This is not about abandoning national grids. It is about adding resilience. When power is generated closer to use, communities gain stability during disruptions, and the system becomes less dependent on single points of failure. The broader point is that decarbonization is a systems problem. Generation, networks, storage, and demand must be designed together. If we integrate them, clean electricity can be reliable, affordable, and scalable. Now, let's address a fear that has shaped energy debates for decades. The idea that society will be forced off oil only when scarcity bites. That story is compelling, but history suggests something different. Major transitions do not usually happen because a resource disappears. They happen because new solutions are simply better. The old system becomes less competitive, more expensive, more complicated, or less aligned with public priorities. Oil is remarkable. It is energy dense, easy to store, and extremely useful for chemistry. Yet its dominance can still fade if alternatives become cheaper, cleaner, and more convenient. Think of how quickly technology can change everyday life once it reaches a tipping point. When a new option wins on cost and performance, behavior follows. That is what planning for the end of oil should mean. Not waiting for a cliff edge, but investing in the innovations and infrastructure that make oil less necessary. The end of oil, in this sense, is an economic and technological outcome, not a geological event. Our job is to accelerate the alternatives so the transition is deliberate rather than chaotic. To accelerate alternatives, we need to be clear about what innovation really is. Innovation is not only inventing something entirely new, it is often the rearrangement of existing knowledge into a better structure. In material science, the same basic ingredients can create very different results depending on how they are organized. Energy systems are similar. The components already exist: renewables, electrification, efficiency technologies, smart controls, storage, and better materials. The question is how we combine them. That is why integrative design is so powerful. If you design a building, a vehicle, or an industrial plant as a whole system, you can remove unnecessary complexity and unlock performance gains that no single component can deliver alone. This kind of innovation is also easier to scale because it relies on engineering and business adoption, not on waiting for a laboratory breakthrough. It can be copied, financed, and improved iteratively. And it can be adapted to local conditions, which matters because energy is deeply regional. Weather patterns, building types, industrial profiles, and grid structures differ. When we treat innovation as system design rather than isolated gadgets, we stop asking what is the one solution and start building portfolios that reinforce each other. This leads to a broader shift. The energy world is moving from fuel to technology. In a fuel-based world, power is concentrated because fuels are traded commodities controlled by geology and often dominated by a small number of players. That is why energy politics has historically been about choke points, pipelines, shipping lanes, and cartels. In a technology-based world, the center of gravity changes. Wind and sunlight are widely distributed. Batteries and power electronics are manufactured, improved, and diversified. Even when critical minerals matter, technology creates options, substitution, recycling, efficiency improvements, and new chemistries that reduce dependence on any single material. Technology also spreads differently from fuels. Once a design is proven, it can be replicated quickly across markets. Costs can fall fast due to learning curves, and mass production. The implication is profound. The future energy system is less likely to be dominated by one cartel and more likely to be shaped by innovation, industrial capability, and supply chain strategy. This does not eliminate geopolitics, but it changes its logic. Control becomes harder to maintain, and competition becomes more about who builds better systems, not who owns a scarce fuel deposit. Of course, technology does not automatically make everything easy. A technology-based transition introduces new questions. Who manufactures key components? Who owns intellectual property? How do we secure supply chains? How do we ensure that new infrastructure benefits communities rather than bypassing them? But compared with fuel dependence, technology offers more degrees of freedom. If one supplier becomes unreliable, markets can diversify. If one mineral becomes constrained, engineers can redesign. If costs rise in one segment, efficiency and demand flexibility can soften the impact. These options are what make the transition manageable. They also point to the importance of circularity. In a fuel world, value is burned once and gone. In a technology world, value can be recovered, metals recycled, batteries repurposed, components refurbished. Circular design is not just a sustainability slogan. It is an industrial strategy that reduces risk and cost. The more we design systems that last longer and can be repaired, the less we depend on constant extraction and replacement. That stabilizes prices and builds resilience. So the best thing that can happen to the energy industry is not merely cleaner generation. It is a shift to an industry that is structurally less hostage to scarcity and more governed by design choices. What, then, should a practical long-term plan look like? It should start with a clear order of operations. First, drive efficiency across buildings, transport, and industry because it reduces cost and makes every other step easier. Second, electrify as much end use as possible because electric systems are typically more efficient and easier to decarbonize with clean generation. Third, build a power system that is both clean and firm, renewables for low-cost energy, storage and flexible demand for balancing, and resilient networks that can handle variability. Fourth, modernize markets and regulation to reward performance rather than volume, so that companies earn value for saving energy, smoothing peaks, and delivering reliability. Fifth, invest in innovation as system design, demonstration projects, supply chain capability, workforce training, and finance structures that lower the cost of capital for proven solutions. Finally, measure success with outcomes people feel. Lower bills, cleaner air, stable supply, and secure jobs. If the transition is framed only as sacrifice, it will fail politically. If it is framed as better services and smarter infrastructure, it can endure across election cycles. Let me close with a reframing. The future is not a choice between prosperity and decarbonization. The choice is between a brittle system that ties our economies to volatile fuels and a modern system that delivers the same services, mobility, comfort, power, production, with far less waste and far lower risk. The end of oil is not a day on the calendar. It is a trajectory shaped by technology, design, and investment. If we do the hard work of efficiency, electrification, and system integration, the alternatives will win on their own merits. And when energy becomes more about technology than about fuels, the incentives shift. Innovation accelerates, costs fall, and power becomes more widely distributed. That is not naive optimism. It is a pattern we have seen in other technology transitions. The task now is to make the transition deliberate, planned, financed, and engineered rather than reactive. We should build the future the way we build good infrastructure. Start with the fundamentals, design for resilience, and align incentives with long-term outcomes. If we do that, the next decades can be remembered not as an era of unavoidable crises, but as the period when we learn to power the world more intelligently.